Hey, thanks for joining me for this Unit 7 test review. In Unit 7, we use a skill that we learned in Unit 5, the skill of factoring polynomials, and we use it a lot. So if you haven't done Unit 5, you probably should go do that first. But good news is, if you didn't really grasp it in Unit 5, when you get another chance here, you're going to see that most of the hard work I do in this recording is going to be factoring. Okay, so we're to find the domain restrictions and simplify and define the domain restrictions. The easiest way to do that is to factor. So we're going to factor first, then we'll try to remember to find the domain restrictions, and then we will simplify. Alright, so I'm going to factor the numerator and denominator. Only need the denominator to do the domain restrictions, but I'll go ahead and do both. And we'll go ahead and do the easy one on top. The numerator is the easier of these polynomials, trinomials. If we have a trinomial in the form of x squared by itself, just 1x squared, plus or minus x times a number, plus or minus another number, then that is the easy way to do this is you take that last number, that constant term, the term without an x, and you break it down into factor pairs, all the different factor pairs. So how do you get negative 6? By multiplying two numbers. And you can be very methodical about this. You start with 1, or negative 1 in this case, negative 1 times 6, and then the next number up, 2, negative 2 times 3, and then it'd be negative 3 times 2, and then you can kind of see that it's the only other option is going to be negative 6 times 1. We can kind of run through in our heads the negative 4, negative 5. Those don't work, and so that's it. Those are the factor pairs. Now, once we have that list of factor pairs, then we add them up and see which pair adds up to that middle number, which in this case is the negative 1, the number multiplied by the x. And that's going to be negative 3 and 2. So negative 3 plus 2, and again, be very methodical. It's a good practice to go ahead and just add them all. Just make sure you're doing this right. And negative 3 plus 2 is negative 1, and so those are the numbers we're going to use. X minus 3 and x plus 2. And I'll leave it to you to go back and check this by the FOIL method, multiply those two factors together and verify that they do indeed add up to the original polynomial here of x squared minus x minus 6. Okay, we'll do a similar method on the second one, the bottom one here. We're hoping that this is also going to turn into two binomial factors. But this was a little bit different because of that coefficient of x squared is not 1, it's 2. There's a number there. So we have to take an extra step. Extra couple of steps. We're going to take the first number, the first coefficient, the coefficient of x squared, and which is 2, and that negative 9, and multiply them together. We'll get negative 18. Then we'll go through the same process of finding factor pairs. That's going to be negative 1 times 18, negative 2 times 9, negative 3 times 6, and then that's it. 4 doesn't work and 5 doesn't work. So we'll keep on going. We'll say negative 6 times 3, negative 9 times 2, and negative 18 times 1. So the second half is a mirror image of the first half of the factor pairs. We're going to look for the one that adds up to that middle number once again. So which of those pairs add up to negative 7, and that's the negative 9 plus 2. But this time, instead of writing those as our factors in our binomial factors, we're going to split this trinomial into two binomials. And we can go either way. So we take the first term, 2x squared, and then the last term will be the same, but the middle term we're going to split up into two terms. Really, we're undoing the FOIL method, if you want to think of it that way. So I'm going to say I'm going to say, just because it'll look neater, I'm going to say plus 2x and minus 9x. So I got that 2x, 2 and 9, no, positive 2 and negative 9 from my factor pairs. They add up to negative 7, and then bring down the minus 9. Okay, so now I have a 4-term polynomial, and I'm going to split. I'm going to bracket this into 2 groups. I'm going to group it. This is the grouping method. So that one, and then there's a minus sign that matches the minus sign on the 9 and the negative 9x. I'm going to put those in the groups, so put a plus sign in between. It's plus negative 9x. It's the same thing as minus 9x. And so I'm grouping those two, and then I'm going to find the greatest common factor for each pair of groups. So each group. So 2x squared plus 2x, the common factor there is 2x. And if I divide out a 2x from just those two numbers, I get 1x plus 1. And for the second group, the common factor between negative 9x and negative 9 is negative 9. So bring out the negative 9 and divide that out, I get x plus 1. Negative 9 divided by negative 9 is positive 1. Now, the x plus 1s are the same. That's what we wanted. The x plus 1s are the same. And so now I'm going to treat that whole thing as one big binomial. So the first term is that whole thing, and the second term is that whole thing, and they have a common factor. The common factor is that x plus 1. So we'll take that out, x plus 1. And when we take that out, divide it out, we're left with 2x minus 9. Now, that method is really elegant. It works really well, and it works every time that it can work. The trinomial can be factored. So if your trinomial can be factored into binomial factors that are have integer coefficients, it's a fancy way of saying that have whole numbers in all the 4 spots, then this method works. So we have x plus 1 and 2x minus 9. Okay. Now whenever we have a number in front of x, we want to think is there a common factor? Can we divide that out? Can we divide out the 2? And no, we can't, because negative 9 is not divisible by 2. So that's it. That's as simple as this gets. Now, it turns out that is the end for this problem. We've factored the numerator denominator, and what we've discovered in that process is that this fraction cannot be simplified. And that's because there's no common factors between the numerator and denominator. So the second part of the question is that's as simple as it gets. We can't do any more. However, we forgot to go back and answer that first part of the question, which is what are the domain restrictions? And we can do that now because we have the denominator factored. So domain restrictions are anything that would make that denominator equal to 0. So what would make 2x squared minus 7x minus 9 equals 0? Now that's a little equation we can solve. We could use the quadratic equation, but we already have these factored. X plus 1 and 2x minus 9. Multiply those together, that equals 0. So then therefore x plus 1 equals 0 is one option, or 2x minus 9 equals 0 is the other. And we solve each of those. X equals negative 1, or subtract 9, 2x equals 9, divide by 2, x equals 9 halves. Okay, now, those are my two solutions to that little equation. But remember, the equation, the purpose of that whole equation, taking the denominator, making it to 0, is to find out not what x equals, but to find out what x cannot equal. If x is either of these two numbers, then that denominator equals 0, and we can't have a denominator of 0 in a fraction, no matter what kind of fraction it is. So those are the two numbers that x cannot equal, and so what we'll say is x does not equal -1, and x does not equal 9/2. And so whatever the context of this problem is, from kind of the get-go, we have to recognize that x cannot be either of those two numbers, because that would make this fraction into an illegitimate fraction, one with 0 in the denominator. Okay, well that was not very satisfying because we didn't get to actually simplify, but we will, I promise, on later problems. Okay, next question. This one I thought was kind of an odd one. I wanted to really kind of take a look at this one. 30% of the cookies in the jar are chocolate chip. I want to increase this percent. There are 10 cookies in the jar now. It's always better to increase the number of cookies you have. The expression below represents the percent of chocolate chip cookies after I add X chocolate chip cookies. We're going to come back to that expression there in just a minute. But let's answer 3 questions. What's the original ratio? The original ratio of chocolate chips to total cookies. So right, the way I put it in the present tense, there are 30% of the cookies in the jar are chocolate chip, and there are 10 cookies in the jar. So right now the total number of cookies is 10, and 30% of them are chocolate chips. That would be 3. So the original ratio of chocolate chip to the total cookies is 3 to 10, 3 out of 10, or 3/10. Now what I'm going to do is I'm going to add cookies to the cookies in the jar, and I'm going to add chocolate chip cookies. Like all the cookies I add are going to be chocolate chip cookies. So as I add cookies to the jar, that 10 cookies, I add some. I'm not going to specify how many, so I'll just say X. And since they're all going to be chocolate chip, then it's going to be X plus 3 also, so that the total number of chocolate chip cookies is going to be X plus 3, and the total number of cookies is going to be X plus 10. That's the, once I've added a quantity of chocolate chip cookies to the jar, that's the final ratio of chocolate chip to total cookies. Now, that looks like this equation here without the 100. So what's going on with that 100? Well, if I do that, I'll get a decimal number, and just as an example, 3 divided by 10 equals 0.3. But if I want to turn it into a percent, I just multiply by 100 times 100 equals 30%. So that 100 is just a way of turning this into a percent instead of a decimal form of the ratio. So I've been writing my ratios as fractions. This formula gives it to me then in a percent form. Okay, and then the last question here is what really is that final number of cookies? And that's an expression. Remember, the number on the bottom is the total number of cookies, and that's just X plus 10. All right, and that's all there is to this problem. Kind of a goofy one, but now we can kind of understand what's going on there. All right, let's get down to some fun math here. Simplify. Now, we have what we have going on here is we have an expression in the numerator that is a subtraction problem, and it involves subtracting a number that's a fraction and a number that's not a fraction. We have an expression in the denominator, and that is also that one's an addition problem, but it's an addition of 2 fractions that are two fractions, and the some of these fractions are rational, meaning that there's x in the denominator. So we're going to simplify both of those. So I kind of circled what we're doing. We're not going to look at this fraction bar in the middle until we have got our numerator as simple as it can be and our goal is to make it into a single fraction, and our denominator as simple as it can be, and our, again, goal of making it into a single fraction at worst. Okay, so in the numerator we have 2 over x minus 1. Now we can't subtract 1 from that, but we can turn 1 into a fraction by just putting 1 over 1. And then we can turn 1 over 1 into a fraction with the same denominator by just multiplying the numerator and the denominator of that fraction 1 over 1 as x. So x over x instead of 1 over 1. And once we do that, we can add our numerators together because the denominators are the same. So that is 2 minus x. Because the denominators are the same, we can add the numerators x, and the denominators are both x, so the new denominator is just x. Okay, so when you're adding fractions and they have the same denominator, just add the numerators together and keep that common denominator. And when you're subtracting, the rule is the same. Okay, so I'm going to put my little fraction bar here. Again, just kind of remind myself where everything is at. But again, not actually doing anything with that fraction bar until we have this as simple as possible. So for the second one, I'm going to do my 2 steps here. I'm going to write on the original problem what I'm doing, and then I'll do it on the next line. So in order to get these fractions to have the same denominator, I just need to multiply each denominator by the other denominator. So I'm going to multiply the 5 times x and the x times a 5. But in a fraction, if you're going to do that, whatever you do to the numerator, you have to, or denominator, you have to do the numerator. So I'm going to multiply that first numerator by x also, and that second numerator by 5. So that I'm multiplying both numerator and denominator of the individual fractions by the same thing. Okay, so I'll write the results down on the next line, or in the next spot. So I have x over 5x plus 10, 2 times 5, over 5x. Now my denominators are the same. I can add the numerators together, x plus 10 over 5x. Alright, and then we'll put in that fraction bar there. And now we've met our goal. That is what we wanted. We wanted to get the numerator denominator to be as simple as possible. And you probably are saying to yourself, not too simple, but that's what we can do. So now we're going to, and I'm going to take this and write it over here so I continue to move left to right. I'm going to write what that problem means. What's that fraction bar mean? It means divide. This is a division sign. So I'm going to write that out. 2 minus x over x divided by x plus 10 over 5x. Okay, now you know that division of fractions is easy. You just multiply by the reciprocal of the number you're dividing by. So 2 minus x over x times the reciprocal 5x over x plus 10. So we just took that second fraction and flipped it on its head. And now we're multiplying, and when you multiply, you're just going to multiply across. But before we do that, we'll look and see if there are any common factors in the numerators and the denominators that we can cancel out. And we do have an x here and an x here that can be canceled. Now notice we also have an x here and an x here, but those can't be canceled because they are part of a bigger thing. It's not just x, it's 2 minus x. And so we would have to have another 2 minus x in the denominator in order to cancel that. Same thing with this x, it's x plus 10. So we need another x plus 10 in the numerator to cancel that. So we end up with 2 factors in the numerator, 2 minus x and 5, and 1 in the denominator, x plus 10. And we can multiply those together if we want to. So I'll go ahead and write it the answer 2 ways. We could just say 5 times 2 minus x over x plus 10, or we could go ahead and do the multiplication and get 10 minus x over, oops, oh my goodness, almost forgot. Horrible job of distributing there. Try that again, oops. 5 times 2 is 10, and 5 times negative x is negative 5x. And then x plus 10 in the denominator. If you want to, you say 10 plus x, just because it looks cooler. But notice that even though we have a 10 in the numerator and the denominator, we've already very well established that we don't have any common factors. Parts of the factors look the same. We've got an x, and now we've got that 10. So it's tempting to start, get a red pen out and start slashing away at things that look the same, but they're not the same. So you have to resist that temptation. So back here, we could see there were 2 factors on top, 1 on the bottom. None of them were exactly the same, and so we can't reduce any further. All right, moving on. Let's try an addition problem. So this one, believe it or not, is slightly less complicated than the previous one. In an addition problem, we have to have the denominators the same issue we had on the last problem. So we're looking at our denominators, definitely not the same and not even close, but I do notice that my denominators are polynomials that kind of look like, if I admit it to myself, they probably could be factored. In fact, that first one, it fits into one of my factor patterns that we learned in Unit 5. And it goes like this. Here it is. It's a squared minus b squared equals a plus b times a minus b. And how do I know that? Because we have x squared, which is a perfect square, minus 16, which is also a perfect square. It's 4 squared. Okay, so that's on our list of perfect squares. Remember, you have a list of perfect squares that you have in your notes that you're working on memorizing. So the factors then would be x plus 4 and x minus 4. Okay, so those are the factors there. And then for my second one, I'm going to have to do the whole, what are the factors of 8? They add up to negative 6. Factors of 8 are 1 times 8, 2 times 4, and that's it. 1 times 8, 2 times 4, 4 times 2, 8 times 1. But none of those add up to negative 6, but you have to remember that if it's a positive number, it could be that all the factors are positive, or it could be that all the factors are negative. So negative 1 times negative 8, negative 2 times negative 4. So there's actually 8 different choices, and it's the negative 2 and the negative 4 that add up to negative 6. So my factors then would be x minus 2 and x minus 4. Now, it seems like it should mean something that we have 2 factors that are the same, x minus 4. And it does. That means that when we're looking to find a common denominator, we don't need to just multiply x squared minus 16 times x squared minus 6 plus 8. That would be crazy. And it would be much harder to do. Well, now we know that they have something in common, so we only need to multiply each denominator by the one factor from the other denominator that's not already present. So that first denominator, x squared minus 16, it has an x minus 4, it has an x plus 4, it just doesn't have an x minus 2. So I'm going to bring in the x plus 2, or x minus 2 and multiply that here, x plus 2. And if I'm going to do that in the denominator, I have to do it also with the numerator. And the same thing with my second denominator. It already has an x plus 2, x minus 2, and x minus 4. So all it's missing is the x plus 4. So multiply by x plus 4. And now my denominators are going to be the same. They are going to be x minus 2, x minus 4, and x plus 4. So each denominator has all three pieces in it. And so when I write my denominators now, I'm just going to write them in factored form just because that makes it easier. So let's rewrite the problem down here with the numerators simplified. In other words, I'm going to do the multiplication here. I've got x plus 2 times x minus 5. I'm going to go ahead and do that. I'm going to do this somewhat mentally. So x times x is x squared. X times negative 5 is negative 5x, and 2 times x is 2x. And so add those together, you get negative 3x. So write that on a piece of paper if you do it yourself, if you weren't following me. And then 2 times negative 5 is negative 10. So I multiplied two binomials there, the one I brought in to get the denominators the same as the x plus 2, multiplied times the existing numerator, which was x minus 5, and I put that in parentheses as a separate binomial. Okay, and then the denominator is my three factors, x plus 2, x plus 4, x minus 4. And sometimes when I'm doing these problems, I won't even write that down just because I'm lazy. Okay, second numerator, 2 times x plus 4. I have to do that multiplication. That's 2x plus 8. And the denominator is x. Did I do that wrong? Oh, I did. I'm so sorry, guys. It's supposed to be x minus 2, and I said x plus 2, and nobody said anything. You guys didn't stop me. So I need to go back and fix, because this is going to be positive 10. Negative 2 times negative 5 is positive 10, and negative 2x plus negative 5x is negative 7x. So I need to fix that. Well, that could have been disastrous. Okay, so let's get that right. That's x minus 2, not x plus 2. Whew. And x plus 4 and x minus 4. So that's a good argument for, going ahead and writing things out. If you write things out and you're kind of copying what you're doing, I found my mistake because I wrote down this factor that I had written up here. I wrote it down, and then I wrote down this factor, and then I realized, wait a second, I didn't just write the same thing twice. So you can catch your mistakes the more methodical you are in terms of just writing everything out. Okay, so once the denominators are really the same, we can add the numerators together. So we're just going to add all those together. And we're just combining like terms. So we have an x squared, and then negative 7x plus 2x is negative 5x. And then 10 plus 8 is 18. And our denominators, see if I can write these properly this time, x minus 2, x plus 4, x minus 4. Now, it's extremely rare that you can go any further. We're going to check it just to make sure, but we'll take the 18 and we'll write down its factors. So 1 times 18, 2 times 9, 3 times 6, and that's it, right? 4, 5, okay. So actually, None of those add up to negative 5, of course, because they're all positive, but if they were all negative, they still wouldn't add up to negative 5. The best option is the negative 3 plus negative 6 is negative 9. So since none of the factor pairs add up to that middle number, negative 5, we know we can't factor x squared minus 5x plus 18. So we can't factor it, so we can't simplify this because the numerator does not have any factors that are the same as the denominators. It doesn't have any binomial factors at all, at least not with integer coefficients. So that's it. Did you like that little use of vocabulary? Integer coefficients just means that there's no binomial factors, there's no factors in the form of x plus minus 2 or x plus 4 with numbers that are whole numbers or integers. Okay, so that's it. That's all we can do. We could take that denominator and multiply it back together, and I will tell you that you would never ever get in trouble for not doing that. That would kind of be a pain in the neck. We would have to go back up here and take x squared minus 6x plus 8 times x plus 4, or x squared minus 16 times x minus 2, and not get the signs wrong, in order to fully multiply those together, but it is always acceptable to leave them in factored form. Okay, moving right along, and we're getting close to the end. We've already seen a problem where we had a problem in the numerator that involved adding or subtracting of fractions, and a problem in the denominator that was similar. This time we're not adding and subtracting, we just have a fraction in the numerator, fraction in the denominator. So remember the rule, that fraction in the numerator divided by the fraction in the denominator is equal to the fraction in the numerator times the fraction in the denominator flipped over. That's a little joke. Yes, but that's what we're going to do. So I'm going to rewrite this as a multiplication problem of two fractions, multiplying two fractions, and I'll flip over that bottom fraction in the process, so I won't have to rewrite this a bunch of times. That would get tedious. It's going to be bad enough rewriting it as many times as I'm going to. So I do want to have this all written out very clearly. So I'm going to write, and I'm giving myself space above, so I'm not going to write this on the first line of my paper. I'm going to write 2 or 3 lines down so that I have some space above. So x squared plus x minus 6, x squared minus 1, that's my numerator, times the denominator, but not the denominator as it's written, but the reciprocal of the denominator. So flip it over, the bottom number on the original denominator is x squared plus 4x minus 5, so I make that my numerator. And then the numerator for the bottom fraction is x squared minus x minus 12, and I make that my denominator. Now, I'm going to do some factoring, and you can see that we've got 4 different opportunities to factor. This would be a terrific place for you to hit pause and to try this yourself. At this point, you should be really good at factoring, but it doesn't hurt to practice. I'll just do them in order. So I'll take that first one there. It just has an x squared, so we'll just do negative 6. Factors are negative 1 times 6, negative 2 times 3, negative 3 times 2, and negative 6 times 1. Add them up to get 1x. That would be those two. So this is x minus 2, x plus 3. Okay, I'm going to cross that off. Denominator, that fits into our a squared minus b squared. That's x squared minus 1 squared. So a squared minus b squared equals a plus b times a minus b. A would be x, b would be 1. And again, this is a great opportunity for you to just multiply those together and verify that that formula really does work even with negative minus 1, because that's sometimes the minus 1 is the hardest one to recognize as a perfect square. It's 1 times 1, it really is. Okay, then the next one we have a negative 5 on the end, so negative 5 would be negative 1 times 5 and negative 5 times 1. Really no other way to do it, and the first pair adds up to 4, so x minus 1 times x plus 5. And last one. Notice I actually haven't done any cheating here, but you can cheat if you want to. I think the methods that we have are so effective, just being methodical, that we don't need to do any looking at the factors that we have to see kind of what potential factors there might be. So I'm not even doing any sort of guessing and checking. I'm being very methodical here. Negative 12 is negative 1 times 12, negative 2 times 6, negative 3 times 4, negative 4 times 3, and that's it. I can stop there once I get the answer. There's only one answer in these. Negative 4 plus 3 is negative 1. Okay, so x minus 4, x plus 3. Okay, so what I meant earlier about cheating is that if you're not really sure on your factoring, okay, so how do I factor that last one? You can kind of guess. So we have an x minus 1 and an x minus 1. And so in the numerator, we wanted one of those three, x minus 2, x plus 3, x plus 5 to cancel out. And so we kind of could guess that one of those was going to be a factor. And the only real choices would have been x minus 2 and x plus 3. So we could have just kind of tried them if we wanted to and see which one works. But again, I think my methods kind of trump those. Okay, so we crossed off the common factors, and there were no other common factors. So we can't reduce this any further. So we just write down the ones that are left. We'll write this all down here. X minus 2 times x plus 5 and x plus 1 over x minus 4. We could multiply those together, and that would be fine. The answer would be x squared plus 3x minus 10 over x squared minus 3x minus 4. And again, it's really tempting to say, I see a lot of stuff that's the same there. Let's cross it off, but we can't do that. I think this answer is fine. Having it in factored form is fine, but this is also correct. Just a quick note on the test, when you're typing in your answers, if you put it in a form, like if you put it in this form and the computer says, no, you're wrong, it was supposed to be in this form, that's the kind of thing that you need to just shoot me a quick email and say, hey, I got it right, because I would give you credit for either form. And yeah, let's see. Did I do that last one wrong? No, I did not. Okay. This is pretty much the same problem. We'll do this one very fast because I'm running out of time, and we just did one like this. So I'm going to do this one a little bit faster. We're going to factor each of these. So this is obviously a perfect square, x squared minus 7 squared. So x plus 7 and x minus 7. And by the way, this is another great opportunity for you to hit pause and try doing this yourself. So I've done the factor pairs for 7, and I decided that x minus 7 and x minus 1. Negative 1 times negative 7 is 7, and plus negative 1 plus negative 7 is negative 8. So if you can do it mentally, more power to you. Factors of negative 3 would be positive 3 and negative 1. Those add up to 2. And then the factors of negative 14, I'm thinking that's positive 7 and negative 2. Those add up to 5. And now we'll take our red pen and we'll cross off the ones that are common. So we have an x minus 7. We could have just reduced this first fraction just by dividing out an x minus 7. That's not really even multiplication, that's just reducing the first fraction. But we have an x minus 1 and an x plus 7. So that first fraction goes away completely, and we're left with 2 binomial factors, one in the numerator, one in the denominator. And you can see again the value of leaving yourself some space above and below the problem. So that reduces your need to rewrite the problem again. All right, well, we made it through. There's one last problem dealing with just taking a formula and solving for a value that the formula is not currently solved for. So right now this formula is solved for A equals, and we want to solve it for H. So we want to rewrite this in the form H equals. Okay, so first of all we say, well, what's being done to H? Two things are being done. It's being multiplied by 2b, so we'll undo that. And it's being added to b squared, so we'll undo that. And we would do this in reverse order of operations. So order of operations says do multiplication first and then do the addition second. So when we're solving an equation, we're kind of peeling back. It's like we're peeling away the layers from the outside to the inside. So we're going to undo or peel off the plus b squared. So we're going to subtract b squared from both sides. So minus b squared minus b squared. That gets rid of that. And so we have a minus b squared equals 2bh. And again, what's being done to h now times 2b, we'll divide by 2b. And if we divide the right side by 2b, we have to divide the left side by 2b. Cancels out. And so we have h all by itself. That's what we wanted on one side. H equals a minus b squared over the whole thing is divided by 2b. Now, this cannot be simplified. If we wanted to, we could break it into two fractions, but that's really not necessary. So we're going to call that good, and that's how you solve a formula for a variable in the formula that's not currently being solved for. Okay. Thank you very much for watching. I hope this was helpful. Make sure you do some practice problems of your own before you tackle this test. It can be tricky, and also lots of scratch paper, and take your time. Don't rush. These are not the kinds of problems that you can just rush through. Thank you very much for watching.